Okay, welcome everybody. I'm Mads Fransen from the Department of Physics, Chemistry and Pharmacy, and it's my pleasure today to introduce our two speakers, Johan Samsing and Daniel Doracio, both assistant professors at the Niels Bohr Institute and the Niels Bohr International Academy. So Johan did his PhD at the Niels Bohr Institute, and he was an Einstein and Lyman Spitzer Fellow at Princeton, I think for 5 years. Until he joined in 2019 as assistant professor at the NBI again. And Daniel has did his PhD at the Columbia University in the US. He's been Einstein postdoctoral fellow at Harvard and is now assistant professor also at the Niels Bohr Institute. And they will talk about, broadly speaking, multi-messenger astronomy for compact objects and compact binaries. Yeah. So probing the universe in electromagnetic, gravitational waves. And gravitational waves, yeah. Please go ahead.
Thank you. Yeah. Okay, which are waves in the space-time. They're very, very difficult to see. Einstein already said that there might be gravitational waves associated with different violent processes in our universe about 100 years ago, but it's only very recent that we have seen them for the first time. That had opened up a completely new field, and I would say that Dan and I, we were lucky to start working on this before it really got really hot. So we have been, had the time to think about this for a couple of years, and it's such a field where there's so many new things happening all the time. So in my talk, which will be the first part of the talk, I'll give a little bit of background, and then I will tell about a new, very exciting source that just has been observed here last year. And then I will tell about how we, with our theories, has been able to put forward a model that might be able to explain where this source is coming from. So my part of the talk will be more on the astrophysical, or on the smaller mass scale of the black holes. Smaller mass scale is about 30 solar masses. That is what we see with this observatory called LIGO. And Dan, he will go up to the really massive black holes that we hope to see in the near future. Massive black holes are millions of solar masses. Okay. So first, a little introductory slide here. Gravitational waves are created mostly from objects, or the strongest gravitational waves are created from objects that are moving very fast and they're very heavy. Okay. If you want that to happen, you need to go to black holes. They can get very close, they can move extremely fast around each other, and they're very heavy. Okay, here's a simulation of two black holes that are merging. You can see, so this 2D sheet is basically space-time, you see, and these wiggles here that are sent out in the space-time is propagating away from the source. You see it's only taking a fraction of a second here, the final inspiral. And this here is the wave front form that we're going to see at our observatories billions of years later, depending on where the source is located. This here is this wave, okay? Time is propagating here. This is the wave. The first part of the movie where it's just orbiting, far away from each other is called the inspiral phase. That phase is out here. And then you have the merger phase. They're coming closer and closer, and then they merge, and then they form a new black hole here. There's a small ringing of the black hole here just when it forms and settling into forming a new black hole. It's called the ring down, and it's a rapidly damped ringing here of the black hole. And you can also see that in some of the data. But this one here was the first observation of a binary black hole mergers only about 6 or 7 years ago. And as you probably know, it gave the Nobel Prize. And this picture here was, most of this picture here were known before that we actually saw the observation for the first time. But what people wanted to see was the actual merger phase here, to see if there was any deviations from what Einstein, he told us that the merger should look like, any deviation from Einstein's gravity model. So far, it seems to be perfectly fine. So I'm not working on that field, I'm working on the astrophysical field, because there's still a lot of different challenges. So with light, as with light, gravitational waves has a frequency. You can think about the gravitational wave frequency spectrum of our universe. And that spectrum, basically reflects what kind of binary black holes that you are seeing and that are merging. Black holes that are very heavy, are very massive, are very big. The sizes are larger, and therefore their associated wavelengths as they're merging are also larger. And therefore you have to, so this is frequency. Massive black holes will live primarily down here in the very low frequency range. Okay? And if you follow one very massive black hole, for example here, the two black holes are coming closer and closer together, and then just merging at some point here. Now, if you look at another black hole, binary black hole that is not as massive, okay, it can still start out with low frequencies, but they can get much closer before they are merging, so they can merge at much higher frequencies. And LIGO, the observatory that people have been working on and saw the first binary black hole merger with, is operating up at these frequencies here. You can ask, why is it this frequency? Well, the frequency is associated with the size of your telescope, and the characteristic size of something you can build on Earth is about 1,000 meters, scale up by some factor. And this here corresponds to, light travel time of, a few thousand meters. So if you want to see something that is a much lower frequencies, you have to build something with much longer arms. They ain't gonna tell about it. That's what people are working on right now. It's called LISA. It's LIGO, just sent up in space, where the arm lengths are, thousands to a million times longer than what we can build on Earth. Okay, so what have we observing so far? We have been observing a lot of different binary black hole mergers. This plot here is maybe not the best, but this is what people normally look at. So it's a good chance for you to just get an idea of how to look at it. Here you have black hole mass, and this is just the number of events that we have seen. And then you should read it in this way, that we have observed two binary black holes here, and then they merge into forming this black hole here, okay? And all of the blue one here are the one that we have observed with gravitational waves. The purple one are the one that we have seen through other ways before that we had gravitational waves. Without going into detail, you see it by if, for example, a star is nearby, the black hole can eat a little bit from the star, and that process can send out some light, and that's a way that you can figure out if there might be a black hole near a binary, near a star or not. So you can see it's a completely different part of the universe, or the population of objects that we are basically probing with gravitational waves. As an astrophysicist, the big question is, where do these binary black holes come from? How do they meet each other? And what can we learn about the whole universe in a larger picture? And that is what I'm working on. So let us think about different ways that binary black holes could form in our universe. Now we have seen them, and we can actually start to test our models. Let's start with these here. If you go out in the night sky and look up, you will see small clumps of stars. It's called globular clusters. They have about 100,000 stars packed into a very small volume. You can imagine that some of if some of these form black holes, maybe because they're so close together, they might be able to link up and then merge. I'll show that's possible later. You can also think about that, well, actually about half of all the stars in our galaxy are binary stars. It's difficult to see with your naked eye, but that's actually true. And you can imagine that if each of these stars are turning into black holes, they might be able to merge within a Hubble time in some way. Okay, so that's another way. Maybe the black holes was formed at Big Bang and just randomly is pairing up in different ways over cosmic time. Could it be something completely different that we haven't thought about? Well, I will tell you about some new models that we've been looking at. Or could it be, in various, chaotic regions where you have stars forming, gas floating around, and that could be in the center of galaxies. Okay, so what can we learn from the gravitational waves, right? So if you're observing gravitational waves from objects here, you have this waveform. And what you can measure is the black hole spins, you can measure the masses, and you can measure the orbital eccentricity. That's what you can pull out from this waveform. Orbital eccentricity is basically a measure of how circular the orbit is when the black holes are merging. Okay, just to give you an example of how this would change the waveform that you're looking at. Here you see the black curve here is a circular signal, two objects just moving around. You have a sinusoidal curve. But if it's not in a circular orbit, you have like this, more like a heartbeat pattern, right? Every time the two black holes get close to each other, pericylinder, you get a burst, and then you have like this, right? So that is one way of measuring one of the three key parameters that you can pull out of this. So just an overview of how those observations are different between different channels. If you have something that's formed chaotically inside a very dense stellar system, black holes are floating around and they're meeting each other in different ways, and at some point they're merging. Well, you won't expect that the spins are correlated, right? It's two black holes that didn't know about each other, they're merging, and the spin orientations are just random, right? And you can also argue that the masses probably are similar, because if you have something that's very light, it might just be kicked out of the cluster through some interaction. So maybe the mass is also similar. Maybe even the eccentricity is non-zero due to that the things are encountering each other on the random orbits. Where in the isolated case, where you have two stars forming together, living its whole life as a binary, it would be weird if there's not correlation between the mass, the spins here, and also if it didn't merge on a circular orbit, right? So you can already see that there might be some hints to that the things that we can observe can tell you about where the things are coming from. Now, a couple of years ago, so I want to take a look at this source here. A couple of years ago, we observed a very weird source. Well, you won't be able to say if it's weird or not from this, but this is the gravitational wave spectrum. And if you go into Wikipedia, it's a very famous source now. So then it basically highlights why it's a very, very interesting source. It has masses, the black hole masses are much more heavy than what anybody would think was possible. If you're asking people a couple of years ago, what is the most heavy mass you can get of a black hole, they would say 50 solar masses and no more than that. This one here had 60 and 85. So it depends a little bit on how you're fitting, but around 80 solar masses black holes. So the first rule of how massive black holes can get, this one just broke that record. It is not even a record, it's just a region where you think it would not be possible. Okay. The next weird thing was that there might seem to be some light associated with it. Why would there come any light out of a binary black hole merger? That's very weird. And the last thing that also seems to be the case is that it was merging on a non-zero orbit. And all of these cases here is something that people would not expect to happen before we saw this source here. And suddenly you see all three things at the same time. What is going on? It's a real observation. Yeah. It's not only theory. So we started thinking about this. Let us take a look at a very dense region of our universe and model it in this way here. This is sometimes, how I normally model things as a theoretical astrophysicist, right? Now all the stars has been put into this gray region, where the outer part is like the halo of the stars are just floating around. And then you have the gray region in the center here. All the heavy objects, they clump to the center. The heavy objects, they interact in different ways. You can form binaries. The stars are coming in, it's being split apart, and things are merging, and things are happening in there. So could there be a way that you could get some of these effects in such a chaotic environment? We did some of the first studies on these black hole scatterings, that we call them. And this is with a semi-relativistic code. It's called the post-Newtonian expansion, not full GR. You'll not be able to do that in full GR. But it's an approximation to Newton's equation, well, to Einstein's equation, where you start with Newton's equations, you're adding things on top. One of the add-ons is gravitational wave radiation. So we have been doing a lot of scatterings of different kind of black holes to figure out what is the outcome of these scatterings, because these scatterings must happen in the center of these very dense stellar systems. Okay, and what we found here is if you already have a binary and a third object coming in, it can perturb the binary here into an orbit where you're like merging on an extremely short time scale. What is happening here is that you excite the eccentricity of this binary black hole that you started out with. In other words, you make it very eccentric, such that the pericenter, the two black holes, almost touch each other. And that will create a lot of gravitational wave radiation, and that will lead to a rapid merger. And you can also see it can only happen because it's in a very elliptic orbit. And the elliptic orbit could explain why the source that we saw was not circular, right? It has some eccentricity. And of course, you can do this much more complicated. I had a summer student working on this problem where we did binary scatterings, because you also have higher hierarchies of mergers that are happening, or interactions that are happening in these very dense stellar systems. And it is actually still ongoing, trying to figure out exactly what's the outcome of these scatterings. But we found a way to calculate, if you're more interested, I can tell you how we did it, but we found a way to calculate basically just with pen and paper what the outcome is of these scatterings. So that has also helped us in trying to understand the outcomes of not only individual scatterings, but whole stellar systems. So you can see here, it's merging here again. So you can get mergers through many, many different ways. However, when we calculate what is the probability of forming a binary black hole with a non-zero eccentricity as a function of how close the two black holes was when they started out, you remember that you have two black holes, another one coming in. So the characteristic separation of the two black holes you start out with is about what we call 1 AU, 1 astronomical unit. Okay, and this graph here shows what is the probability for something to happen as a function of that distance. And if we go here, the triangle here shows the outcome where you will be left with some non-zero eccentricity when it's merging, when we see it in LIGO. And you see the probability here is 1 to the 10 to the minus 3. Okay, so this is the cluster case here. So 1 in 1,000 scatterings will create something that's not circular. So that's not really very encouraging, since this is only maybe source number 20 that we have seen, and we already see it to be highly eccentric, plus it has all the other weird properties. So it probably didn't form in a cluster, even though that we are probably on the way to something that could maybe explain this non-zero eccentricity. So what about something else? Okay, so then we thought about, could it happen in some other regions of our universe where the things are not happening, in a 3D cluster where things are moving around as we saw, but still something like a place where it's very dense, where you have a lot of things going on. We thought about, what about the center of galaxies? And then we considered the following model. Let's consider in the center of galaxies, Dan gonna tell more about a supermassive black hole. And in these centers, you have a massive gas disk. That is something that has been observed. We're not coming up with this. That has been observed. And we know for sure that you have tons of these in our universe. What we did come up with, and we did work with other people on with this particular model as well, was that it could be there are black holes in this gas disk. Could be from stars forming in the disk. It could be that this disk simply captured in black holes. And then what happens, and there was a lot of people looking at that point, is that the black holes pairing up, they start to scatter off each other. You basically have the same process as we looked at in the cluster, but not in a 3D environment, but in a 2D plane that's close to what you have for the disk. Just stand over here. To make a long story short, could explain the high masses? Probably yes, because if you start out with something with a lower mass, say 30 solar masses, it could build up to a very high mass by keep merging throughout the disk. So it can build up to high masses through successive mergers. Light that was observed for this source, probably yes, there's a lot of gas. If you have a merger inside the disk, could create some light through the interaction with the gas. The eccentricity, that's the last piece of this puzzle. Could we be able to form something with a higher possibility in a disk versus the 3D cluster that we looked at? So we did the exact same scatterings as I showed before, but constrained the scatterings to a disk And we found the probability of forming a highly eccentric merger jumped from down here, it's a 3D environment, all the way up here. You can see here, you're about 20-30% chance for making a highly eccentric merger if you're interacting in a 2D plane versus a 3D cluster. So we put out this, we calculated, we were able to estimate it by hand as well, and said, well, this is probably the first evidence of a binary black hole that formed in a AGN disk, and we were able to put that final piece into this puzzle here. And this here is a supermassive black hole. Here's the disk, and here's the 3 black holes. And it will, in a couple of days, appear in Nature, so we are very happy for that, so you can keep an eye on that. This is only the start. Gravitational wave observatories now, they're working, it's great. Europe is also building much larger observatories, and with the Einstein telescope, for example, we'll be able to see every single merger in the entire universe. We'll see 100,000 of mergers every single year. So this is just the start of this field, and it's not the end of this talk, because now Dan is coming up. Thank you.
Thanks, Johan. All right.
Can I ask a first question?
Well, I think that we're going to ask the question afterwards. Oh, yeah.
So you say the gravitational waves
Yeah.
at the speed of light, and
Yeah.
I guess that's in empty space.
Yeah.
What about near the black hole? I mean, is the speed reduced there?
I would say it's the speed of light anywhere. Yeah.
Okay.
But there might be some effect, right, where they're taking a different path. So if you say, for example, that you have a massive galaxy or a massive galaxy cluster, and you have a black hole merger, that is, so you're sitting here and the galaxy cluster is here, and the black hole merger is behind the galaxy cluster, it can lens or bend the gravitational wave signal. So you will see part of the signal, and then maybe a couple of years later, you will see another part of the signal. And people have already been starting to look for these kind of double mergers. So maybe in a couple of years, we're going to see the same signal like appearing one more time. That's a gravitational lens effect.
But I was just wondering how it's kind of emitted in the first place. There's no this kind of Cherenkov-like effects playing a role where the object is moving at a speed comparable to this gravitational wave, and then you have this.
Well, we can talk more about it. You definitely also have like gravitational wave boosting, red shifting, and blue shifting. So you see effects.
And lensing,
so you
but
definitely see
gravitational wave Cherenkov. I'm not sure. Actually, it'd be interesting to think about.
But it's a very good point.
Yeah, but I will mention some gravitational lensing in this second part of the talk. Maybe not in detail, but that's something Johan and I have worked on too, is the gravitational lensing of not only light but gravitational waves. But I want to continue now on what Johan started and talk about this new interesting field of gravitational wave astrophysics, and now move from these amazing events of stellar mass black hole mergers that we've observed with LIGO, and start moving up the mass scale to the possible mergers of supermassive black holes at the centers of galaxies, which we have not detected yet. But to start, I want to start here, just the electromagnetic spectrum, to try and reiterate a point that Johan made. So this is the electromagnetic spectrum. Almost everything we know about conventional astronomy is from observations of photons in this spectrum. All right, here's a view of the Milky Way, counting stars since the beginning of science. And of course, that picture in the optical and the visible is just one small part of the electromagnetic spectrum. And every time that we invent some new technology to observe a different part of it, to observe the universe in, for example, X-rays or gamma rays or radio, we usually discover something quite interesting and new about the universe. And so I won't go into all these pictures here, but for example, first time we looked in X-rays, we saw gas falling onto black holes, some of the first evidence for black holes, and some new pictures that you might recognize on the right. There it is. But my point of this is that there's an electromagnetic spectrum, and now that we've observed gravitational waves, you can also start talking about or thinking about the gravitational wave spectrum in a very similar analogy. So this is kind of a complicated number line here of what the gravitational wave spectrum we think that might look like. So on the left, we have, sorry, I have the wrong button for the laser pointer. But on the left of this, there we go, is really low frequency, long wavelength gravitational radiation. And on the right is the high frequency, short wavelength gravitational wave radiation. And so here, this realm of the gravitational wave spectrum encompasses everything that Johan talked about in the first part of this talk. This is the kind of frequencies of hundreds to thousands of hertz that LIGO can detect. But just like an electromagnetic spectrum, we can look to different parts of this gravitational wave spectrum, which we're working on doing now, specifically going to lower frequencies. And so these lower frequencies at millihertz and nanohertz will probe a whole different part of the electromagnetic sky, the low frequency gravitational wave sky. And so what's there? How can we detect, what instruments are we building to do this, and what's there? I want to say a few words about that before we go any further. So Johan mentioned this experiment called LISA, the Laser Interferometer Space Antenna, and this will be a really scaled up version of LIGO in space. These 3 satellites shooting lasers back and forth between each other, trailing the Earth orbit with 2.5 million kilometer interferometer arms. And so when millihertz gravitational waves pass by this experiment in space, it'll be able to detect these gravitational waves from a kind of changing length between the 3 satellites. So this is LISA, and this will be something that will come up in the 2030s. So we have about a decade or so before this happens. But there's also this kind of fascinating experiment called the pulsar timing arrays. And so instead of building a gravitational wave detector, so LISA, we'd build this 2.5 million kilometer interferometer in space. Instead of building one, we can use a galactic scale experiment where we put clocks all over the galaxy, or we have clocks all over the galaxy. We time those clocks very precisely, and we say if a gravitational wave is passing through our galaxy, like right here, the timing of those clocks will go off will be off from each other in a correlated way. And so we don't actually put clocks there, but we use these astrophysical clocks called pulsars, which are neutron stars that are spinning on a very stable spin orbit of order milliseconds that we can watch. And by timing all of these spinning pulsars throughout the galaxy, we can look for these really long wavelength, low frequency, and nanohertz gravitational waves. So that's how we're going to try and probe this part of the low frequency gravitational wave sky. But what's there to find? And that's, to me, the exciting astrophysical part. So let's see. Black holes in the universe. You have a really big star. It goes supernova, and it collapses into the stellar mass black holes that Johan talked about in the first part of this talk. And if 2 of those come together and merge, say in a globular cluster or galactic nucleus, we see the gravitational waves in the high-frequency LIGO detector. But we also know that there are these supermassive black holes with 100,000 to 10 billion times the mass of the sun that exist at the centers of most galaxies. We have pretty good evidence that they're there, including a picture of one from the Event Horizon Telescope. And when 2 of these merge, you guessed it, these are what are going to create the low-frequency gravitational waves that LISA and LIGO can detect. However, we have the same problem as with the stellar mass black holes. How is it that they're astrophysically paired together to merge? What is causing the merger of these supermassive black holes? But let me be clear, we have not detected gravitational waves from these yet, so why would we expect to? Well, this is one observation. There are supermassive black holes at the centers of galaxies. Another simple observation with this artist representation here is that galaxies merge. So if galaxies that harbor supermassive black holes merge, the question is, do the black holes then come together and merge? And this question might seem simple, but it's kind of at the heart of a major open question in astrophysics that I will describe quickly here. And it takes 3 steps. So the first step, these galaxies with supermassive black holes merge. And when they do that, the 2 black holes sink to the center of the new galaxy essentially from drag from all the gas and stars in that galaxy, bringing them to the center. And this is something, a process that we have observational evidence for. This is an overlay of X-ray and optical images of a galaxy that has recently merged with its two accreting supermassive black holes highlighted in blue here. So we know that this happens on the large scales. And then on the smaller scales, if the two black holes, after they've sunk to the center of the new galaxy, can get close enough, they'll emit gravitational waves very, very vigorously. And that emission of gravitational waves will cause the two black holes to merge, and that's also how we will see them with LISA and the pulsar timing arrays. But the step that I've left out kind of encapsulates this open question. There is some question of what exactly happens in between. We have a good theoretical picture of what happens on the large scale and the small scale, but in between, we're still asking and working on understanding how exactly these supermassive black holes, two of them, interact with their environments to come together and get close enough to merge, or not. And a key to solving this question is, of course, understanding how this binary does interact with its astrophysical environment at the centers of galaxies. And a lot of the work that I'm doing is thinking about one specific, very important, ubiquitous environment is gas at the centers of galactic nuclei. So this is a simulation of two masses, two black holes, orbiting each other with a gas disk falling onto them. And so by understanding this process, what do we hope to learn? Well, one, understanding how the binaries interact with this gas and then are either driven together or not, right? Very similar to how you have a satellite moving through the Earth's atmosphere that will cause its orbit to decay and fall into the Earth. We want to understand how that happens in this slightly more complicated case. And what this will do, understanding this interaction with the gas, will help us build models of what the population of these supermassive black hole binaries should look like out in the universe, which will help us do a number of things. One being predict what is the rate of gravitational wave events that we'll see with something like LISA or the pulsar timing arrays. But on the other side, you can make predictions, but you should also have a way to test those predictions. And this type of modeling, this gas binary modeling, can also help us look for these systems. Because not only have we not seen gravitational waves yet from the merger of these, we've also not identified them at these very close separations with any messenger, with electromagnetic radiation either. And so one goal is to use this type of modeling to predict populations, but then also to figure out a way that we can uniquely identify these systems, which has been a difficult problem to date. So I just want to, in the time remaining, talk a little bit about what we're thinking about, how to do this, how to find these systems in this kind of uncertain step 2, if you remember from the earlier slide, to find evidence for these supermassive black hole binaries when they're in this very kind of unknown stage of their evolution. Because if we can find them there, we learn about how it is they are coming together to merge or not. So one idea that I work on a lot is what I'll call periodic light curve searches. And let me quickly say that one reason why this is so difficult to find these with regular telescopes is that they're so far away and they're so close to each other in their orbit that we can't resolve that orbit. We can't take an image of that orbit and just watch this picture of a binary going around itself over time. There's actually some possibility that something like a future event horizon telescope would have the resolution to do that, but that's probably further down the line. So what we rely on are these indirect methods to find these systems, and one of these indirect methods goes something like this. So here's a cartoon schematic of what a quasar, or an active galactic nucleus that Johan talked about, looks like. Essentially, it's really bright. We see it to the edge of the universe because there's gas here, this little pink donut, falling onto a supermassive black hole. When it falls onto the black hole, it heats up, and we can see it very far away. The game that I'm playing is replace that with a supermassive black hole binary that we think should be there, and ask, how does that look different? And one way that it might look different is that as you look at this quasar, this active galactic nucleus far away, the light from it isn't just kind of steadily, stochastically flickering, but it's being modulated very strongly at some period which you would associate with the orbit of the binary. So this idea has been put into play over the last half a decade or more, where a number of big surveys looking at hundreds of thousands of quasars over a decade, looking at the light curves of these quasars over that period of time, have tried to identify if there are any such periodically varying systems. And so here, I just wanted to show you, there's about 100 to 150 of these candidate periodically varying quasars in the sky. And I've put them here on an axis of what period we seem to observe versus the central mass that we can measure independently at the center of those systems. So this is interesting, but we can't quite start talking about demography or learning about populations of binaries from this because we don't know that these are actually binaries. So a lot of what I think about is there any way that we can come up or think about a kind of unique smoking gun signature that would say which of these oscillations, these periodic light curves, are due to a massive binary and which are due to something else. So to answer that question, you have to ask, how does a binary make such oscillations in a light curve? Well, one way that we found from these simulations of gas falling onto a binary is that as the binary orbits, which you can see here in this kind of two-dimensional density distribution, it accretes gas at a varying rate, meaning the rate at which gas falls onto it is varied at the orbital period of the binary. And that rate of gas accretion can translate directly to how bright this object looks over time. So I'm not going to spend much time on this except to say this is something we're still thinking about. How can you link these observations to this type of measured accretion rate? But there's, I think, a lot more work to do here. What I want to say is that even if you don't have variability from how the gas is being accreted over time, if, as sometimes you find, the gas looks pretty steady, it's accreting steadily onto your binary, then there's still a way to get these periodic oscillations simply from special relativity and general relativity alone. Effects that are called the relativistic Doppler boost and gravitational self-lensing, which I just want to show a picture of what I mean by those effects. So let's look at this for a moment. Here's us. We see some binary black hole far away. Here's the smaller black hole, here's the larger black hole, and it's inclined to the line of sight by some angle. This orange thing shows that this smaller one is accreting gas and it's bright. And so what does this brightness from this smaller black hole's accretion disk look like over time? If it were just sitting there, it would look steady. We would just see steady light, a flat line in this curve here. But because it's moving quite quickly, up to perhaps 10% of the speed of light on its orbit, the Doppler boost tells us that as that black hole is moving away from us, like this blue dot is here, it looks dimmer than the rest frame. And when it's moving towards us, it looks brighter than the rest frame. So this kind of simple observation can tell you that, can give you this type of oscillating light curve, directly from special relativity. And there's also some very interesting predictions that this will make for multi-wavelength observations that I could talk about later, that make this even a more powerful diagnostic. But even more exciting than that, I think, take the same setup, but now have this binary even closer to edge-on, so that it's almost orbiting edge-on to your line of sight. Then you still have this Doppler boost effect, but each time this blue dot, the accreting smaller black hole, passes behind the larger black hole, the light coming from its accretion disk is gravitationally lensed by the larger black hole, and it creates these really wild-looking symmetric flares at these specific points in this Doppler light curve. So this would be something that would be pretty close to a smoking gun evidence for gravitational lensing and Doppler boost in a supermassive black hole binary system. Okay, and I thought maybe I'd show you kind of a face-on quick rendering of what that would look like if you could resolve this system. So bloop, each time this smaller disk surrounding the smaller black hole goes behind the larger black hole, it's warped, and that makes the system look brighter during this flare. All right, so how much time do we have left? So to wrap up, I just want to say that you can calculate then, this is really unique looking, but you can also calculate that it should happen relatively often. And I won't go into those numbers, but I will say we have a really strange looking actual candidate right now that we've been looking at for the last 2 years. So this is a real light curve. This was found by the Kepler mission, which is looking for exoplanets. And because it was looking for exoplanets, it had a really, really high cadence, looking very often, and with very, very good precision, photometry precision. So an accidental find from something that Kepler just observed is this really strange light curve that someone brought up to me at one point after giving a talk on those predicted light curves that I just showed you. And so we decided to see if this kind of shape could fit these self-lensing models. And so what I showed you before were for circular orbits, but if you make these orbits eccentric, you can get something that kind of looks like this. And so if you zoom in on this flare, you see that it is nice and symmetric, maybe with some strange structure here. So just as an exercise, we said, well, can we fit our self-lensing model to this system and see if it predicts when this flare would repeat? And so we did that, and we made a prediction. And I'm sorry, I'm just going to leave you, so I'll say that we did only learn about this system a few flares later, according to our model, if it is actually a binary. But we proposed for some time to look for this flare in this window here, and we have some data now, over 1.5 years. And I'm sorry, I can't show it to you yet, but hopefully next time. It's interesting, but I can tell you we didn't necessarily detect a flare yet, but there are some interesting constraints on the model. So I'm happy to talk about this more as well. And then let me just wrap up and say that this is hopefully not the end. This kind of thing is something we can look for with these upcoming all-sky surveys, such as this one here, the Vera-Rubin Observatory, and its large survey of space and time, which we've, with some theoretical models, predicted that this should see. It could see up to tens to maybe 1,000 of these types of self-lensing light curve systems, and that's a study that we recently did based on piecing together cosmological simulations and models for binary decay to get to these types of numbers. So I just want to end by saying that we have not detected gravitational waves from these low-frequency supermassive black hole binary systems, but we're going to soon, actually, with the pulsar timing arrays, maybe in the next few years, with LISA in the next decade. And right now, we can keep working on trying to find evidence for these systems with electromagnetic radiation. And piecing all those pieces together will really help us to learn about the lives and evolutions of the biggest black holes in the universe. So, thanks. And happy to take questions on any part of the Odyssey today.
I guess that helps. All right. Try to avoid the echo. Thanks for the talk. Great. A little better.
Yeah, I just needed. Okay, there we go.
All right. Thank you. So one question I have is how do you model these black holes in the simulations? I do remember some of your papers where you have like a Newtonian gravitational description, but then you add on top the orbital evolution, right, from the perturbative expression. Is that still what you're discussing here?
Yeah. So from the hydrodynamical simulations you're mentioning, yeah. So for the large part, these are still Newtonian orbits that we use the Newtonian orbit we fix it on a Newtonian orbit, and we measure types of accretion rates and forces on the binary that will give us what the orbital decay should be. And we do that over a range of all the possible binary parameters we can think of to get a first order fix on how should this binary evolve and accrete. And this is really in the simplest picture with kind of the fundamental physics that we want there to start. It's just the hydrodynamics and the gravity to tell us how does even in that case it's kind of been difficult to understand how does the binary evolve. There's a debate right now on whether the gas, even in the simplest 2D hydrodynamical Newtonian case, whether the gas pushes the binary apart or brings it together. And so we've really been focusing on that simplest case with a lot of physics that needs to be added on.
Mm-hmm.
So if
okay, just to follow up, I guess.
Yeah.
So it makes a lot of sense to focus on the orbit as a salient feature, right, of how gravity comes into play here. But if you look at other models that have magnetic fields that treat the black hole as an extended object, right, it may be compact, but it's not a point source, then you get these jet emissions, for example, and they can be on a much larger scale. So you had, for example, OJ 287 on the slide, and just to mention, the Event Horizon Telescope is not only looking at event horizons, right? That we also looked at jets. OJ 287 in 2017, and if you look at that source, it's not clear to me whether the orbital motion is the first observational signature. It may well be for other sources, but sometimes you may see the jets first, and they require different models, and I can send you some links.
Yeah, I completely agree. I skipped the slide giving an overview of all the ways we can look, and I think that's a fascinating one. When you have these jets, which we can't approach in the simulations yet, and how these jets might be twisted or cause features of the orbital motion. I think that's just as viable. It's really interesting. It'd be great to talk about that.
Yeah, I had a question for Johan's part. So for your model where you have the merger within the AGN accretion disk, so I was just wondering, LIGO Virgo sky localization is of course not awesome, but it's sort of it gives you some area, and then if I remember correctly, you get the distance from the gravitational wave signal itself. So that gives you sort of a volume in which you should have an AGN. So I'm just wondering whether you have candidates in there, in that volume. Oh, in that volume? Yeah, for that particular signal.
There was a lot of uncertainty of if this is associated with this one here, right? So it is not clear. But I think that the only thing that was kind of the thing that made these people put out that paper, and we were not part of the light paper. That there was another paper coming out just with the light itself, and that was just due to the fact that the things seems to be happening at more or less the same time. But you cannot say, oh, it happened in exactly that galaxy, and that AGN seems to be, it seems to be over there fitting the properties of this source and so forth. It was just, broadly matching. Maybe, I think it's on Wikipedia, it's like hundreds of square degrees off, or uncertain, right? But it was a point that it was, like almost at the same time that made people think that it could be associated with it. And that seems not to be the case with any of the other sources that we have seen, or they have seen, right? But you're absolutely right. It could be many other things in terms of light. It could just be that you're lucky or not. Yeah, either lucky or unlucky that it was something else that just happened at the same time.
And I might add.
But add something. Further.
I don't remember the details, but there has been some work done asking if in the future, when we have a larger catalog of events, can we match that with the catalog of AGN to see if there's a statistical matchup between event localization, which isn't great, and AGN location? So that could be.
That's a good point.
All right. I'll try to close. So so if there are no further questions, I think we should give a big round of applause for Johan and Daniel first. And if I understand correctly, there's a bit of a refreshments now here, right? Or upstairs here, or yeah. And we might go upstairs later on for a chat. You're welcome to join, and maybe we'll also later on go back to CP3 Origins and have a chat there. Anybody's welcome to join. Okay.
Yeah. Thanks so much for having us.
Thanks a lot for coming.
Yeah.